let's give it another try, okay? Let's give it another try. So we have beginner level examples, intermediate level examples, advanced level examples. I would usually go for the intermediate level examples. I mean, Boolean, not Boolean, and maybe that's gonna demonstration, structural imbalance, copy clone open source code to run demos for solving known problems in a DWave system. Let's jump into intermediate level. That I might just be burning my fingers here. Because we've covered that in the demos. So how to represent an AND gate, how to represent an not gate node, but like we did the AND gate with the truth, the table of truth. Let's just do map coloring. I think I'm familiar with the problem. I know that's a sort of a traditional computer science problem as well, where basically it gives you a set of constraints on how to color a map, and you have to then basically color the map in a way that it satisfies all the constraints. So it seems to feed what DWave is supposed to be able to solve, which is constraint satisfaction problems, or CSPs. So map coloring. This example solves a map coloring problem to demonstrate using Ocean tools to solve a problem on a DWave system. Constraint satisfaction problems require that all problems variables be assigned values out of a finite domain that result in the satisfying of all constraints. The map coloring CSP, for example, is to assign a color to each region of a map such that any two regions sharing a border have different colors. Okay, so that's already given by the problem statement. So you can't color two adjacent countries with the same color. Example requirements. So we're going to have solution steps. So I'm not going to do that right now because I don't have. I think it's pointless for me to have it all set up, as I already have the feeling that's not the kind of quantum computing intuition that I want to sort of focus on in the future. But basically, solution steps. Let's try to confirm that. So following the standard solution process described in section, we saw that. Yeah, so we need to formulate a problem as a binary quadratic model, BQM, by using unary encoding to represent the C colors. Each region is represented by C variables, one of each possible color. Okay. So we have a given amount of colors, and then basically the way we encode that is we, for each region, we just have all the colors set to 0, and then whatever color we pick for that region set to 1. So formulate the problem as a graph with provinces represented as nodes and shared borders as edges using 4 binary variables, 1 per color. Create a binary constraint satisfaction problem and add all the needed constraints. Convert to a binary quadratic model, sample, and plot a valid solution. So I think that's going to be a good example. That's going to be a good example because we know there might be a solution, or there might not be a solution, but we don't know the solution yet. So what I was saying before with the AND gate is, you know what values you want. So you know how you have to encode that because you're taking your inputs and outputs as part of the way you define the energy function, right? So in this case, Canada using 4 colors, and we've got 13 provinces, and the postal codes are here. Blah, blah, blah. I set constraints, and so to set up constraints and convert the CSP to a BQM. Start from the problem as a graph. Okay, so the provinces, and then we have the neighbors, right? So those are the nodes, and then those are the edges of the graph. Then we move on to create a binary constraint satisfaction problem. Good. So that's why the interesting part comes in. CSP Okay, so we add a constraint called one color configurations. Represents a constraint that each node select a single color. Okay, so that's yeah, that makes sense, right? So basically each, how do you do that though? One color configuration. So okay, it basically says you can pick one of the 4 colors. This one. So this one, this one, or this one, right? So those are the 4 possible configurations, basically. None of these 3 colors and this color. The next constraint is that 2 nodes with a shared edge, they can't have the same color. Not both one. So let's take a look at the code. One color configurations. I'm assuming, okay, so here we prepared, I don't know where is that all coming from, the variables and this. Okay, so this is defined in here. So, oh, so the constraints are represented as function, as set of functions. Return not VNU. Okay, so given VNU, and then it can be that they have the same color. Valid configurations, one color configurations, colors is equal the length of that, so 4. Then for each province, add constraint at each node, select a single color. Okay, so you have to actually go through the provinces, variables equals, okay, for range colors. I don't quite get what it's what is it actually doing, but add constraint one color variables. Oh, okay. Ah, I get it. Okay, so basically what this I'm a bit stupid. So basically what this is doing is saying it's generating all the possible colors that a province can choose, and then this constraint is telling from this set just pick one. Kind of. Yeah, whatever. Probably not, but whatever. So and then add a constraint for each pair of nodes. They must not be 1. Okay, so basically you go through all the neighbor edges and then you say, so those are the variables that you have, and add the constraint that they can't have the same color. So that's what we defined in here. Okay. That makes sense. What else? Yeah, then basically sample that stuff. So you tell it sample 50 times. You need matplotlib to show the results. And then you basically plot the sample. Okay, so it's just a function to plot the sample. Yeah, and here you have the solution. So yeah, that's, I mean, I'm happy that was an intermediate level. That was definitely not that complicated. If you just know the basics, I mean, yeah, it's just it's what I say. So basically, what this is saying is, if you're able to express your problem in terms of constraints, then Mr. DWave can solve it. In terms of a CSP problem, then DWave can solve it. You just have to know, yeah. So I think, and then it's when the documentation makes sense, because if you want to know how to, for example, this is really problem specific how you do that, right? So in this case, I'm quite sure that I'm quite sure there's other ways to represent the problem. This is probably the most straightforward and also easy to code. Yeah. And then the way this works is the DWave basically gives you the tool set to transform that into the BQUM, or however that is called, the binary quadratic thing model, and that is already the then the input for the computer. The thing is, haven't I missed something? I feel I'm just missing something. Convert the CSP into a binary quadratic model so it can be solved on a DWave system. Bam. Done. Okay. Okay. Yeah. Can you do more interesting stuff with it?